Hello everybody, how are you doing? I thought we'd finish off the B part, so actually the whole contest, for the 2011 Csmc today. So we're going to finish off question number 3, that's the last question on the contest. How about we take a look at it? We're expecting it to be the hardest question on the contest, since it's the one in the final position. So we're going to have our wits about us. So let's take a look at question 3. So suppose that n is greater than 3. A sequence of a1, a2, a3, all the way up to an of n integers, the first m of which are equal to -1, and the remaining p equals n minus m of which are equal to 1, is called an MP sequence. Okay, so minus 1s and positive 1s, that's where we're getting the m and the p from. All right. A part, the sequence -1, -1, 1, 1, 1 is the MP sequence A1, A2, A3, A4, A5 with n equal 2 and p equal 3. Consider all of the possible products AI times AJ times AK with I less than J less than K. So these are being multiplied together, but they're in a specific order. So consider all the possible products that can be calculated using the terms from this sequence. Determine how many of these products are equal to 1. Okay, seems straightforward enough. How many will there be? Well, we have 5 numbers in our sequence, and we're choosing 3 of them in a particular order, because the order of the numbers being multiplied doesn't actually matter, so we're specifying a particular value by saying that A has to be less than, or I has to be less than J, it has to be less than K. So 5 of them, each product we choose exactly 3 distinct ones. So if I choose 3, there should be 10 different sequences. So 10 isn't that bad. How about we write them out? So we grab ourselves a new piece of paper. So our sequence was -1, -1, positive 1, positive 1, positive 1. Okay. So like I said, there will be 5 choose 2, which is equal to 10. Possible products. For any sequence for these products, you would have n choose 3, but we have specifically 5 numbers, so it's 5 choose 3. So we could try A1, A2, A3. I want to write these out, but I want to do it in a very methodical way. So we're going to keep A1 as long as possible. A2, A4, A1, A2, A5, A1, A3, A4, A1, A3, A5, A1, A4, A5. So those are all the possible ones we can have with 1 in the front. So now we're going to start putting 2, A2, A3, A4, A2, A3, A5 onto the next page. I want to leave this space here for my actual calculations. A2, A4, A5, A3, A4, A5. And if we count them up, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, that's all of them. So this is -1 times -1 times 1. That's going to be 1. -1 times -1 times 1. That's going to be 1. -1 times -1 times 1, that's going to be 1. -1 times 1 times 1, that's going to be -1. -1 times 1 times 1, that's going to be -1, and this one will also be -1. -1, 1, 1 again. And then finally, we're just going to have a 1 times 1 times 1. That's equal to 1. Now, what exactly were we asked for? Determine how many of these products are equal to 1. Okay. Equal to 1. So, let's go back to what we worked out. Well, we have 4 of them that are going to be equal to 1. this one, this one, this one, and this one over here. Okay. Either we use both A1 and A2 to cancel each other out and become a 1 with another 1, or we have no negative ones at all. Okay, so that can only happen if we choose both of these, and then we have one choice for the other one, so that's 3. Or we have none of these, and we have to choose the remaining 3 numbers altogether, so that's just one choice there. So 3 plus 1 is 4. Alright, so we have 4 products that are equal to 1. Fantastic. And that's all we were asked for in part 1. Determine how many of those 10. Well, we've got 4 of them. B. Consider all of the products, AI times AJ times AK with I less than J less than K. Okay, same as before. That can be calculated using the terms from an NP sequence of n terms. Determine the number of pairs MP with 1 less than or equal to M, less than or equal to P, less than or equal to 1,000, and M plus P less than or equal to 3, for which exactly half of these products are equal to 1. Okay. So in terms of M and P, and possibly even N, so those are the 3 variables we've got, can we determine how many of these are going to be equal to 1? Is there an expression for that? How many of these are going to be equal to negative 1? Because you can only have product be 1s or negative 1s, because of the way we have set up our MP sequence. So how do we get 1s here? How do we get negative 1s here? Okay. And we want exactly half of these products are going to be equal to 1. And we have a couple other conditions we need to satisfy. So let's write down the conditions we need to have satisfied, so that we have them on hand. 1 less than or equal to M, less than or equal to P, less than or equal to 1,000, and M plus P greater than or equal to 3. M plus P, of course, is going to be N. So we might need to use that relationship. Okay. So for an MP sequence, the first M are negative 1. First M are negative 1. The last P of them, which is just the difference between the total number and M, are going to be 1. So it's going to look like 1, or sorry, negative 1, negative 1, negative 1, and there's going to be M of these. 1. And there's going to be P of these. Okay. AI, AJ, and AK are equal to negative 1 or 1. Okay, that product definitely going to be negative 1 or 1. So to get a product of negative 1, either we have AI is negative 1 or AJ, AK is 1. Or we can have AI, AJ, AK are all equal to negative 1. That's the only way to multiply 3 numbers from amongst negative 1 and 1 to get a product of negative 1. So we know we need 1, negative 1, but so you may be wondering to yourself, well, yeah, we need either 3 negative 1s or 1 negative 1 and 2 positive 1s. Why can't we have AI be 1, AJ be negative 1, and AK be 1? Well, the reason is, the way the MP sequences are set up, the negative numbers all come before the positive numbers. So if I know that AK is negative 1, that means that AJ and AI must also be negative 1. Because because AI and AJ come before AK. So if you have a negative 1, everything before it had to be a negative 1 as well. Okay, and that would contradict the fact that we only need 1 negative 1 in this case. All of them being negative 1, that's a completely separate thing. So by the same token, if you want a positive 1, you need to either have 2 negative 1s and a positive 1, or all 3 positive 1s. And if you have you could choose AI and AK to be negative 1s, but the second AK is a negative 1, AJ would be a negative 1, and that would be a contradiction. We need AJ to be positive 1. So the only possible way this works for an MP sequence, because remember IJ and K are in order, is AI, AJ being negative 1 and AK being positive 1. Okay, so these are the 4 possible cases, and we're not choosing anything else here. So what we can do is we can set up an equation. We can count the number of times this case happens, in terms of, I guess, M and P. We can count the number of times this case happens in terms of M and P, add those two up, and that'll be the same as the number of times this case and this case happen. So how many times can we choose all 3 of them to be negative? If we know all 3 of them are negative, then we're choosing from M of the negative numbers, and we're choosing 3 of them. If we're choosing one of them to be negative, then we're choosing one of them from the M negative ones and 2 of them from the P positive ones. So we know that that's going to be the same as choosing all 3 positives and then choosing exactly 1 positive. So P choose 1. Out of the positive ones, we're choosing 1. And out of the negative ones, we're choosing 2 of them. Okay? So we have some nice choose notation here. But we have now we have an equation we can actually work with rather than just stating facts about the possible products. We have an equation in M and P. Maybe we'll get some more equations later on. Or maybe we can manipulate this one to give us a relationship between M and P. So what does this notation mean? Well, what's the best way to do it? So let's say B choose C. So if you've never seen choose notation, b choose c, written like this. It's b factorial over c factorial over b minus c factorial, which is the same as b times b minus 1 times all the way down to b minus c plus 1 over c minus 1 over 1. So that's one way of writing it. So that tells us that this equation right here can be rewritten as m minus 1, m minus 2 over 3 times 2 times 1, which is 6, plus m choose 1, so that's m over 1 times p minus 1 over 2 times 1. And that's going to be equal to p minus 1, p minus 2 over 3 times 2 times 1, plus p choose 1, so that's p divided by 1, and m minus 1 all over 2 times 1. Okay, so we have some cleaning up we can do. We could multiply everything through by 6 and get a common denominator. We could also group these m's together or rearrange some things. P minus 1. I don't want to turn these into cubics yet if I don't have to, because cubics are hard to work with. Okay, so what can we do here? I think the best thing to do would probably be to get it all on one side. Certainly, and then maybe we can group some things together. I mean, maybe I'm going to have to expand these cubics out. I really don't know. I'm hoping that I don't, but it's looking like I probably will. Yeah, let's just go for it and expand them out. So that's m cubed minus 3m squared plus 2m plus 3mp squared minus 3mp. We're bringing this stuff over to the other side. So minus p cubed plus 3p squared minus 2p, then minus 3m squared p plus 3mp equals 0. Okay. Let's just double check to make sure that's correct, because this is exactly why I didn't want to expand out the cubic. I just need to make sure everything's fine. Okay, and these two guys will cancel out. So that'll be nice. We'll use the purpley color, the deep purple, the navy blue, whatever you want to call it. Actually, you know what? That doesn't really stand out enough. We'll go through it again with the red. Okay. So, there's no decent thing that I can see to do other than I'm noticing that basically I have the same thing written above and below, except m's are swapped with p's. And everything here is negative. So, what I might do is I might group by powers. And obviously, you can see the way that this is set up, you're going to have a great deal of symmetry. That basically this top statement is and this bottom statement are nearly identical. Just the m's and the p's have been swapped. So what I'm going to do is I'm going to not group by like terms, but I'm going to group by similar terms. So I'm going to go m cubed minus p cubed. And I'm going to group that together because it looks very similar. And then we're going to do minus 3 m squared minus p squared. Okay, and maybe some of you can see what we're doing right now. 2m minus p plus 3 mp m minus p equals 0. And you'll notice that each of these is going to have a factor of m minus p, so we can take out m minus p. That's going to be a pain to factor, but I think it's m squared plus is it mp? How do I factor that one again? I think it's minus. So that'll give me m cubed minus m squared p, and that'll give me minus m squared p. So m cubed plus m squared p minus m squared p. And then we're going to have p squared here. Minus 3 mp m plus p, that's just the difference of squares, plus 2m minus p plus 3m minus p mp equals 0. Okay, so now that we've noticed we have that m minus p there, we can sort of, it's in every term, so we can completely take it out. I'm going to use the big square brackets here. So m squared plus mp plus p squared. Gosh, what was it on the other side? Minus 3m plus p. Plus 2, I think, and then was it a plus or was it a minus? Plus 3mp. Okay. So I think I've got it. Now, let's just double check. So that's fine. Different ways to choose those. That's great. That's fantastic. We're doing excellent. Choose notation. Yeah, that's fine. That's when you multiply by 6, so that all works out. Fantastic. It's always a good idea if you've done a lengthy calculation before you keep going, before you start manipulating it any further. And on the other sheet, we have it sort of in a nice semi-factored form. So before we commit to factoring completely the quadratic on the other side, it might be a good idea to make sure it's the correct quadratic. Okay. M cubed, yep, minus p cubed, minus 3, and then we have the m minus the p squared. Fantastic. M minus p again with the plus 2, and then plus 3 mp, but that should be a p minus m. And we have an m minus p, so there's a little something wrong here. And this is exactly why it's good to go back and check these things. So that should be a minus 3. And that should be a minus 3. And I think everything else, yeah, that was fine. I took the MP out of here. We double checked that that worked. That was easy to take out. So if I multiply this through, I get minus m. Yeah, so minus 3m mp, so minus 3m squared p. Minus 3 minus p, so that's 3p mp, so that's 3mp squared. Okay, so that works, and I guess we have to change this guy to a minus. That's nice, and so we have that factor out there, and these guys at least cancel each other out a little bit, not so much with the other ones. But at least now we might be able to write this whole thing on one line. Hey, what do you know? We did. Okay, so it looks like we have two options so far. I mean, we could keep factoring this, although it's going to be a little harder because it's not like we have another n minus p that'll pop out. But we can definitely keep factoring this. Or we could stop and say, hey, m minus p equals 0 would definitely solve this. So we could try m equals p for some solutions. So putting m equals p with our other properties, we had what? 1 less than or equal to m less than or equal to p less than or equal to 1,000. We want m plus p greater than or equal to 3, otherwise how could we choose 3 elements? And we want p and m to be equal. So combining these two, I can just say 1 is less than or equal to p is less than or equal to 1,000. And since we know p is equal to m, then we know what the value of m is. So that simplifies those two. Now how many of these p values solve this? So p has to be greater than or equal to 3/2. And p is an integer. So we'd have to say p is less than or equal to 2. So 1 won't work, but the number of numbers here is 1,000 to minus 2 plus 1. And we can work that out on our calculator. It gives us 999. So right now we have 999 possibilities, and that's when m is equal to p. Fantastic. Now, how about m and p that solve this equation right here? And keep in mind, anytime m is equal to p and it also solves this equation, we're going to have to exclude that because then we'd be counting possibilities twice. Okay. So we ask ourselves, what if m squared minus 2mp plus p squared minus 3m minus 3p plus 2 equals 0? So that's so far the other way we can solve this. A better way to phrase that might be, okay, we solved the m equal p case. So if m is not equal to p, then we need this to be equal to 0. Okay, so we reduced our workload. Now we're working quadratically, whereas before we had a cubic that we factored. So is there any other way to factor this? Well, I admit there's still some symmetry here. But my suspicion is that we're not going to get a nice factorization here. But now that we're at a quadratic level, what we can do is we can say, let's solve for things in terms of, do we want m or do we want p? Who would be better to solve for? M is less than or equal to p, so is there going to be a better one? Use a quadratic formula. Probably want positive values. Let's solve for things in terms of p, and this is just me thinking ahead. Because of the high degree of symmetry here, it doesn't actually matter I'm solving for p so that p will be greater than m, because we know that p is greater than or equal to m. So we're looking for p greater than m, and I'm gonna you'll see as we go along. I'm going to sort of rearrange this so it's a quadratic formula in terms of p, so that p we'll use the quadratic formula. We'll solve for it in terms of m, and because p is greater than m, I think we'll be focusing on the plus, not the minus, when we do plus minus. Now, if you didn't catch that, if you don't know where I'm going with it, that's fine. That's me thinking ahead, and I want to use p because I want my solution to be a little more elegant. Solving for m makes absolutely no difference. It's really okay. Minus 2mp, and I think that's all the p's we have, plus m squared minus 3m plus 2 equals 0. And what we see here is we have a quadratic in terms of p. P squared, and then, oh gosh, what was it? I just saw it on the other page. Minus 3 minus 2m, so that's minus 2m plus 3p, and then we have m squared minus 3m plus 2 equals 0. So we have a quadratic in p. We can solve for p using the quadratic formula, and then we'll have another relationship between m and p, just like we had before when we said m equals p, and we got a whole bunch of solutions there. So p is going to be equal to negative b, so that's going to be just 2m minus 3, plus or minus the square root of b squared. We can ignore the minus sign because minus 1 squared is just 1. So 2m plus 3 squared. Minus 4a, which is 1c. m squared minus 3m plus 2. All over 2a, which is 2. Okay, so that's, well, this 2m and this 2 will cancel out to be m plus 3 plus or minus, and that's why I'm going to choose the plus, because we need to add to m to get p, because p is greater than m. Okay. So that's going to be 4m squared plus 12m plus 9 minus 4m squared, so that cancels out, that's great, plus 12m plus 8. Now let's double check, just because this 12m, I would hope that it actually canceled out with that 12m. I mean, we might not be so lucky, but I mean, the 4m squared's canceled out, so it would be really nice. So we had this equation. We copied it out correctly down here. P squared minus 3p minus 3m, 2 m squared minus 2mp. It looks like this is going to be right, so we are going to have some more m stuff here. So those cancel out. So I'll use the red because apparently the purple doesn't show nicely. And then we're left with 24m and then 9. Oop, that should be a minus 8. 9 minus 8, so that's plus 1. All over 2. Okay. I guess it still could be negative a little bit if this was small enough. Okay. So m and p are positive integers. Okay, fantastic. What does that tell us? Well, that tells us that this square root thing, we have to be square rooting a square. So 24m plus 1 needs to be a perfect square. Not only that, it must be an odd square. Okay. Okay. So let's say suppose that 24m plus 1 is equal to 2k plus 1 squared. This is what a general odd number looks like. And then 24m plus 1 is going to be the same as 4k squared plus 4k plus 1. 24m is going to be 4k squared plus k. 6m is going to be k squared plus k. Does that help us in any way? I don't think that really helps us, does it? Okay. If k is odd, then we still have even on the right-hand side. If k is even, we still have even on the right-hand side. So this 6 isn't really telling us a whole lot. What if it was 3? So if k was divisible by 3, then this would be divisible by 3. If k was congruent to 1 mod 3, then we have 1 plus 1, that'd be 2. And if k was congruent to 2 mod 3, we'd have 2 squared, which is 1 modulo 3, and then plus 2, so that'd be 3. Okay. 6m is, whoops, one too many symbols. 6m is congruent to 0 mod 3. So if k is congruent to 0 mod 3, then k squared plus k is congruent to 0 mod 3. If k is congruent to 1 mod 3, k squared plus k is congruent to 2. If k is congruent to 2 mod 3, then k squared plus k is, that's 1 plus 2, so that's going to be congruent to 0. So k cannot be in the form 3t plus 1, but it could be in the form of anything else. And it occurred to me right now that that's not helpful. Because that'll mean that 2k is congruent to 2, and then when we add 1, it just means that this is not a multiple of 3. So you know what? We could probably realize that in a different way, so let's just ignore that. So I goofed. I went down the wrong rabbit hole here. Much easier to just write. let's go over to the other side and clear that page. So while all this analysis is correct, it's getting way too much into modular arithmetic. I think there's a faster way to state where we were approaching. Alright, so it needs to be an odd square and not a multiple of 3, so we're narrowing down our options here. Now it's an old job interview question to show that every odd number squared that's not a multiple of 3 is of this form. So let's see if I can remember how to do that. So, how do we do this? Okay, so if k squared is equal to 24m plus k, then k squared minus 1 is equal to 24m. So we just need to show that 24 is a factor of k squared minus 1. K squared minus 1 is k minus 1 times k plus 1. So these are the two numbers around k. K is odd, so we can be assured that 2 divides. If this number is odd, let's say it's, 17. K is odd, K is 17. Then we have 18 and we have 16. Notice that one of those is a multiple of 2, it's just an even number, and the other one is a multiple of 4. And this happens with every odd number. Okay, if you have an odd number, then the two numbers around it, and one has to be a multiple of 2, the other one's going to be a multiple of 4. This always works. Okay? The easiest way to show that is k odd implies that k is 2l plus 1. So k minus 1 is equal to 2l. K plus 1 is equal to 2l plus 2. K minus 1 is equal to 2l. K plus 1 is equal to 2l plus 1. L and L plus 1 are consecutive. So 1 is a multiple of 2. If you have any two numbers in order, exactly one of them will be a multiple of 2. If you have any three numbers in order, one of them will be a multiple of 3. Four numbers in order, one of them will be a multiple of 4. This is sort of a basic number fact. that we don't need to state we're on the senior paper. They're assuming grade 11 or 12, so we sort of are expected to know these sorts of things. So 1 of k minus 1, k plus 1. Well, really all we need to know is therefore 8, which is 2 times 4, divides k minus 1, k plus 1. Okay, we don't know which one is the multiple of 4, which one's the multiple of 2, but we do know that that happens. So we get 8 in total here. We can guarantee that k minus 1 times k plus 1 is a multiple of 8. Now, since 3 does not divide k, and we have 3 numbers in order, that means that 1 of k minus 1 or k plus 1 must be a multiple of 3. Again, I don't know which one, but I do know that there's a multiple of 3 in there. And that means 24 divides k squared minus 1. So what does that tell us? Well, we're trying to find values for this 24m plus 1. I know it's actually been a little while, several minutes, since I've been talking about our original problem. I've been starting to talk about odd squares. But we're trying to find integer values for the square root of 24m plus 1. That means it's got to be a square. It's clearly not even, either because we need it to not be even and because this plus 1 means it's not even. So it's got to be an odd square. And since it's 24m plus 1, and 3 is a factor of 24, we know it can't be a multiple of 3. But that's okay. Every other odd square that is not a multiple of 3 is of this form, so we're all set. We now know all the possible squares that we could be having. So, one thing I can notice is m is not going to be equal to 0. So 24m plus 1 is going to be at least 25. And this is either going to be negative 1 or well, here. The point is so the square root of 24 plus 1 is greater than 3. But we know that p is going to be greater than m. And p is equal to m plus 3 plus or minus square root of 24m plus 1 all over 2. This means we can ignore all the or minuses in the plus or minus. Right? Anytime we would minus square root of 24m plus 1, it's going to be greater than 3, and that means we would get a negative value on the numerator, therefore a negative fraction, and we'd be having p is m minus something. And p is supposed to be greater than m. Okay. With all that said, we could probably make a little bit of a chart. So 24m plus 1, m And I guess p would probably be what we want to do. So we're looking for odd squares that are multiples, not multiples of 3, so we're looking at 5 squared, so that's 25. Probably be easiest to write 5 squared. No, 25. 5 squared equals 25. 7 squared equals 49. Not 9 squared, so 11 squared equals 121. 13 squared equals 169. Not 15 squared, that's a multiple of 3. So we need the next odd square, so that's 12 squared equals 289. And let's see what values of m and p we're getting here. So that's m is 1, 2, 5, really? 120 divided by 24. Yeah, it's 5. That's kind of odd. I don't know why it skipped over. 168 divided by 24. That's 7. 289 minus 1 divided by 24. That's 12. So we're starting to get a whole bunch of sort of really random values for m. Values of p that will work. So that's 3 plus 5 divided by 2. That's 4. 1 plus 4 is 5. 3 plus 7 is 10 divided by 2, so that's 5. 2 plus 5 is 7. 14 over 2 is 7, so that's going to be 12. 13 plus 3, that's 16, so 8, that's 15. And this one here is 22. So it just keeps going on like this. Now these all are satisfying what we're talking about, because 1 is less than m, is less than or equal to p, is less than or equal to 1,000. M plus p definitely more than 3 in all these cases. So the question is, we need p less than or equal to 1,000. Where do we get that from? And then we need to find a way to count all these up. So we need to know where to stop, and that's p going to be less than or equal to 1,000. So at 1,000 is sort of where we need to stop. Okay, so how might we figure that out? What to do? Well, we could guess some really large numbers. That might do it. I'm not noticing really a pattern going on here. Well, except 5s, 7s, 12s, 15s. So is the next one 15? How about 19 squared? So that's 361 minus 1 divided by 24. Is that going to be... It is 15. So the p from some sort of k squared is equal to 24m plus 1. Is the same as m from, if we go down 2 from the list. So, plus 4. Or not plus 4, it should be plus 6, right? Yeah, we go down the list by 2, we've shifted the whole thing over. If m is less than 1,000. So let's figure out where m is less than 1,000, then we can go back to and say that's where p is less than 1,000. So if m is less than 1,000, then 24m plus 1 is equal to 24,001. So square root of 24,001 is approximately 154.9226. So let's try 151, 153 squared, 155 squared. See what m's and p's we get out from there. This one we can't allow divisible by 3. So 151 squared minus 1 divided by 24, we get 950 for m. How about 155 minus 1 divided by 24, we get 1001. That's definitely too big. Now with this 950, we'd have 1027 for p, and this one here, 1001 plus 158 divided by 2 plus 1001, we'd have 1080. So let's check these. So our rule is if we find an m value, if we go back 2 rows, so if we subtract our square by 6, then we should get the same p value. So 151 minus 6, 145 squared, and then 155, so that's 149 squared. So what m value does that give? Oops. So 145 squared subtract 1 divided by 24, 876, and then add to that plus 148 divided by 2, we get 950. Exactly as predicted, this one will be 1001, and 149 squared, subtract 1 divided by 24, 925. 5 squared up to 145 squared. If we can figure these out, then we should be home free. So what's the best way of doing this? So 145 minus 5, that's going to be 140. Does that help us with anything? It'd be great if they were different by a multiple of 3. Alright, but they're not. Okay, this is so between 3 and 147. This is a span of 3. Being multiples of 3 very important here, so what I've done is I've widened my net to odd squares between 3 squared and 147 squared. It doesn't change my tally, but it certainly helps me count. So 147 minus 3, that's going to be 144 numbers. One half of them are odd. So that gives me 72 odd numbers. 2/3 are not multiples of 3. And that's why I chose a span of multiple of 3. That way this fraction is going to turn out to be just fine. So 72 divided by 3, that's 24, times 2, that's 48. Now every m and p we already remarked in this group, this other factorization satisfies all the rules. 1 less than or equal to m, less than or equal to p, less than or equal to 1,000. M is less than p. That way we're not double counting any previous cases. M plus p is greater than or equal to 3. I mean, our lowest one is 1 plus 5 is equal to 6. So we're all set. All we had to do was count them, and you could count them any way. This is the way I chose to count them. If you wanted to write them all out, I mean, it's only 48 numbers, so it wouldn't be too tricky. But as you can already see, this question's a tad time-consuming. So this gives us a total of, well, how many did we have before? 999 plus 48, and that's 1,047, I think. Yep. Possible m and p. Now let's go back and make sure that I actually answered what we were asking for and didn't misread the question. Because if I misread the question, I might just pull my hair out at this point. Determine the number of MP, and half of these products are equal to 1. And yeah, it seems like it's been a while, but yep, half of the products were equal to 1. That's how we set up our equation in the first place. And we factored it. We got a whole bunch with m equal to p, and then it was just this really weird quadratic at the very end. So I would guess that the first one, A, was probably worth 2 marks, and this might have been worth 8 marks. So definitely there was a lot to justify in B part. But we got our final answer of 147. And so that about does it for question number 3, and that was the last question on the CSMC. So that concludes the 2011 paper. Thank you so much for watching. Thank you for making it all the way through this video. If you have a simpler way to do any of the calculations or any of the simpler reasoning behind any of the problem solving in this one, I would love to hear it in the comments below. I really would like to know your thoughts on this one. Did you get this question? Did you do it a different way? I would love to know. Because frankly, I thought this one was a tad long. Good question, just a tad long at the end. A lot to work out with that last quadratic key factorization. But overall, a nice first Canadian senior paper, and hopefully you've liked it, and you will join me as I look at the other ones in the future. So thank you so much for watching, and I'll see you guys next time.